and the organizers to invite me to give a presentation about our recent work. Yeah, in this talk, I want to speak about our framework to estimate the extinction time and particularly the distribution of extinction time of infectious diseases in mean field approaches. It's not directly related to COVID, and I think that's probably a main focus of this program, but I think it's quite general, and I hope I can convince you that it can be used for different diseases. Oops. Yes. This is a work I did particularly with Kat Rock and Matt Killing in the Spider group in Warwick as a part of NTD modeling consortium. Yeah, I mean, with a lot of help and support from people in Warwick and in other groups, particularly for this work with support from Ron and Chingy in the group. The work is motivated by an example of sleeping sickness, and that's why I give an introduction about it. But we see later that the model itself is quite general. Sleeping sickness is one of the neglected tropical diseases, which is threatening a big population in sub-Saharan, especially in DRC. It is a vector-borne disease, and it's transmitted to humans by TETC. Infected humans go into two different stages, and they would unfortunately die if they are left without treatments. However, our knot is close to 1 for this disease, and thanks to the recent programs in DRC and in general in Africa, this is the disease is I mean the prevalence reduced a lot, and now it's targeted for elimination by WHO. Diagnosis and treatments are done through two different processes. People can go to medical centers if they have symptoms, or there are also some mobile teams that go to villages at risk, and they test people who or volunteer to participate in the program. This disease has been studied in the spider group for a long time, and there is a model that considers the details of transmission and the screening program of the disease. The model considers two different human populations at different levels of risk, and it's like a compartment model. There are different compartments for different stages of the disease. I don't go into detail, but just want to show you that the details of infection dynamic is considered both for TETC and for human. There are two versions of the model available: a deterministic model and a stochastic model. In the deterministic model, the dynamics are described by differential equations, and in the stochastic models, dynamics between different populations of humans are described by stochastic events. This hat deterministic model actually comes hat deterministic model comes with a lot of advantages, and it's an advanced model, and it comes with a lot of flexibilities. For example, it's time efficient, and it makes it easy for the fitting programs. At the moment, it's been done with MCMC methods in the group, and for different regions, like name health zones, the fitting is done based on the number of screened people and the number of cases reported. Here you can see on the left side one example of the fit for a health zone called Mosango in DRC. And fits actually work very well, and then it helps us to come up with a lot of information about the disease dynamics in different regions. For example, here you can see a distribution of reproduction ratio in different regions, color-coded, for the regions that data is available. Yeah, the main point is to emphasize that the ODE models come with a lot of advantages and they are strong. And I should also emphasize that there is a good agreement between the ODE version and the stochastic model, even at low prevalences. However, there is a fundamental problem in extinction in the ODE model and in general, I think in these mean field approaches. If we look at the number of new transmissions or the number of infected people, if reproduction ratio is smaller than 1, it would decrease over time. However, it never reaches 0, although it's very small. And a threshold is needed to define the extinction or the endpoint. And different values of thresholds are used in the literature for different diseases. Even for HAT, for example, there are very different values. Of course, it's obvious that if we use different values of threshold, we can come up with different estimates of the elimination year. And a main question would be, what is the correct value of the threshold that should be used in this, in ODE models? And for that, we thought first we would use a stochastic model to define the threshold. The stochastic model of HAT is based on the deterministic model. It considers human population with real integer numbers, and the dynamics are described by stochastic Poisson events. And since the populations are, since the populations are described by integer numbers, we can define the endpoints clearly in this stochastic model. Here you can see one example. It's actually not the the real situation. Is for a smaller population, just to see the point. And we see, for example, the number of new transmission is changing stochastically over time, but in average it's decreasing because the reproduction ratio is smaller than 1. And at a certain time it reaches 0, and we can define elimination of transmission. For the HAT, actually we'll look at the time period to make sure that elimination of transmission happens, because it's slow and vector-borne disease. This is, however, just one realization. We need to repeat it. We need to repeat it for different realizations, and we can get a mean curve here shown in black. And we can also calculate the mean elimination year by just analyzing elimination for individual curves. And then we can estimate threshold as the number of new transmission in the mean elimination year. We did it for HAT for different parameter sets, the posterior parameter set, and also for different regions, and we came up with different values of threshold. Sorry, I forgot to say, if there is any questions, please interrupt me. Feel free to interrupt me. Yeah, and yeah, here actually we came up with different values of thresholds, and that's why we decided to start a simple approach to estimate, to understand better what it means and how we can estimate the extinction time in deterministic model. We use a simple SIS model, and writing the dynamics with this equation, and in the limit that susceptible population is not that different from the total population, which is the case for hat, we can simplify this SIS model with a birth-death model. Here, birth corresponds to infection, and death is like treatment, diagnosis and treatment. Just for a second, we can focus on a simpler case when there is no birth, and starting with n infected people, we see that in the mean field, we have a mean field solution that number of infected people is decreasing exponentially with time with such an equation. Yeah. And then we can estimate the average extinction time, and we know that when we start with n infected people, we can go to n-1 state within the time of 1/dn, and that actually gives the estimate of the average extinction time by this series. And then we can calculate the extinction threshold as the number of infected people at the average extinction time. And it is actually, for this simplified death model, effective death model, is given by Euler's constant. Now let's come back to the birth-death model. Again, when birth ratio is smaller than death rate, which corresponds to reproduction ratio smaller than 1, I decreases exponentially with time in a mean field solution. And then we can also estimate the extinction time if we are in the state of n infected people. In the next step, we can go to n+1 or n-1 with probabilities proportional to B and D. And then we can write this relation for average extinction time, which can be simplified with this equation, and it gives us a matrix that can be inverted to calculate tau n. Here we can see the extinction time plotted as a function of initial number of infected people. As we expect for large n, we see a logarithmic behavior with n, and of course the extinction time increases with B. Here the birth rate shown in different colors. Yeah, and we can also estimate the threshold with this relation as number of infected people when at the average extinction time. And this threshold value reaches a plateau as n increases, as we kind of expected. And if we normalize it by 1 minus E/D, all the curves collapse on top of each other for large n, which is, and the value is given by the Euler's number. And it makes the life easier. We have like a well-defined value for the threshold based on B and D. We can challenge our model and to calculate the the error bars and the prediction intervals, similar to the mean field, similar to estimating the mean extinction time. We can look at the second moment and it can be given by a relation like this for the second order, which is simplified to such a relation, to such a simple relation. And again, we can inverse the matrix and calculate the second moment for different values of n. That gives us the error bars. We can continue and we can go to higher moments. Fortunately, we can come up with a simplified relation like this that can be solved numerically, and we calculate different moments of the extinction time. Here, the second, third, and fourth central moments are plotted as a function of n, not exactly s, for different values of b. And what we are interested in is actually estimating the distribution. Having all the moments, we can estimate the distribution, but here we use the first 4 moments and match it with an F distribution, which is quite a good fit for this problem. We calculate the distribution of extinction time for any B and D. And it helps us to also come up with the prediction intervals. Let's compare the, this model, the estimated F distribution, with the solutions of a stochastic model. Here, for example, we did like the forward equation, the Kolmogorov forward equation solution, which are plotted in bars, shown in bars here, and they are compared to the estimated F distribution in the colored curves. And we see that actually they fit very well. So the F actually, our method can provide a good estimate of the extinction time, the distribution of extinction time. Here for 2 different values shown, and 2 different values of B, birth rate. And we can also compare the predicted intervals, and they agree quite well. In the lower plot, you can see the F distribution plotted for different values of B. And as we increase B, the distribution is shifted to the right as we expect, and it also broadens. I promised at the beginning that there are applications to more sophisticated models like G-hat dynamics. We compared this estimate with the solutions of G-hat. First, actually, we use an ODE, the ODE solutions of G-hat dynamics calculated numerically to estimate birth and death rates. So we have from the solutions, we can plot the number of infected people and, for example, new transmission as a function of time, and the ratio between new transmission and infected population will give us birth rate, and the exponent of these plots in a logarithmic scale would give us B minus D. So we can calculate B and D from ODE solutions. And then we estimate the F distribution, the distribution of extinction time here shown in purple lines. And then we compare it with the solutions of stochastic models of hat shown in bars. And we see actually that our estimate, our model provides a good estimate of the distribution of extinction time, although it's a sophisticated model. I should mention that here we didn't use the real numbers of active screening. It's like just a constant active screening. yeah, we can. I mean, the two plots here actually correspond to two different health zones with two different prevalence values and two different dynamics of jihad. You can also see that the average extinction year is quite different between these two. However, this approach can provide a good estimate of extinction time for these two parameter sets. Of course, for each, we have different health zones, and for each health zone, we have a posterior of parameter sets, and they give different dynamics. Here, actually, I compared the threshold that we calculate from our approach. I mean, this SIS model approach or Bertet model, and compare it with the threshold that we estimate by comparing stochastic and ODE solutions. And we see that, we see that this model can give a good estimate of the threshold for different parameter sets, and even it captures quite well the stochastic fluctuations of the threshold for different health zones. Yeah, that's also the threshold values that we hope can be used later for in ODEs for estimating extinction time. Yeah, with that I come to the conclusion. I hope I could convince you that this simplified model based on that model can provide good estimates of distribution of extinction time and thresholds for different models, and it agrees with the solutions of stochastic models, for example, the forward Kolmogorov equation, or more sophisticated models as sleeping sickness model, as far as the dynamics can be captured well with SIS model. Yeah, I mean, all the analysis here is for the HAT dynamic is done for a constant active screening level. However, it changes in the real data, and our challenge for future is actually comparing the real screening levels with those simulations with this model. Yeah, as I said, the threshold, if we have like a threshold value, we can use it in the ODEs later easily, and we can have, for example, maps of extinction year based on the threshold that is needed. I would like to thank all the collaborators, of course, Kat, Drog, and Matt Killing, and also Chingy, Ron, and Chris in the group, and the whole Spider team, and our collaborators in Swiss TPH and WHO and Penalty HA, and of course the funding from the Gates Foundation. Yeah, that's the end, and thank you also for listening.
Right, thank you. Right, if you could unshare your screen, please.
Oh, sorry, I should, yeah, I should unshare.
Should be an end sharing choice somewhere.
Yes, yeah.
Oh, okay, thanks very much. All right. Okay. Do we have any questions. Maybe start with any questions on the details. Anyone else there? I mean, I think the thing that interests me is was the just thinking of the data, was the estimated R values all being sort of in a fairly narrow range, close to 1. I sort of wonder if there's some sort of artifact of that causes that, whether it's really the case that all these areas are sort of so close to extinction.
You mean for sleeping sickness?
Yes.
I think actually HAT is the dynamics of HAT is believed to be very slow. And that's the case even without, screening program. That's what we know about the disease itself. Yeah, probably it's also related to the, to the vector-borne nature and all the rates and the population.
Yes, I'm just wondering how our number depends, how the R number sort of works in two population models that just I'm not so familiar with. So other practical question about sleeping sickness would be: are there other animal populations that could keep the disease going if we get rid of it in humans?
Yeah, that's actually an important question, and there is a study in the group trying to address that. But there is a potential role of animal reservoirs.
Is that domestic animals primarily or wild animals?
I guess domestic, but I'm not 100% sure. Yeah,
I think if it's domestic animals, then you probably have more control over it if you need to try and eliminate it in.
Yeah, but I mean, now the group is also looking at it, and yeah, it seems not to be like super, important or critical. It just, they can play a role, but yeah, we are not sure how important the role is. But it seems like the human infection is more important.
Yeah. And how widespread in Africa is sleeping sickness? Is it?
At the moment, it's mainly in DRC, and it also exists in some other countries, but it's not that big. But at the moment, in the last several years, there were a lot of fundings and screening programs that help to decrease the level.
Yeah. So are there particular examples of countries where the prevalence was higher and has been eliminated
yes.
or nearly eliminated?
Yeah, I'm really bad in names, but even in DRC, I know there is a region, there is a state where it was very big, and now it's called Ecuador. That it decreased significantly and it's close to elimination. But I think I'm worried if I say something wrong, because I'm more like in the modeling part, and yeah, I'm not very good in remembering the name.